Hello, ladies and gentlemen out there. We have made it. We are at the end of our 1968 Ontario Senior Contest. We're on the last question, question number 13. It's been quite a journey getting here. And what have we got for question 13? A multiplicative group, apparently they did group theory back then, is made up of n plus 1 distinct elements. We're going to label them A0, A1, A2, all the way up to AN, where A0 or A0 is the identity element. I'd personally prefer to call it E, but that's just the way I was raised with group theory. Other people probably want to call it 1. Anyways, if it is given that AI squared is equal to the identity, so that is, so first thing I notice, that means that every element is its own inverse. That's kind of cool. Prove that the group is commutative. Prove that AI times AJ is the same as AJ times AI. Okay, and they also want me to write down the multiplication table for this group in the special case where n is equal to 3. Okay, I can already fill in at least that part. Because if n is 3, we would have, I'll write down the Cayley table here, A0, A1, A2, A3. So if I just have 4 elements. Now if A0 is the identity, we can fill in everything here pretty quickly. Okay, and since A1 times A1 is the identity, everything is its own inverse, we can fill in that pretty quickly. Now, we should be able to work this out. Now, whatever I put here, since it's commutative, I'll also put here. So that'll be really nice. But what should go there? So it's almost sort of like a Sudoku in the sense that because it's a group, I can't have A2 here again. There's only one way to make A2, and we've already got it. So I can't have A2, I can't have A1, and I can't have A0, so this has to be A3, and this has to be the missing A2, and this has to be A1. Okay, otherwise, you'd get duplicates in a column or a row, and that wouldn't be a group. That wouldn't even be a quasi-group. Probably would still be a semi-group, though, if you know what I'm talking about. But because it's commutative, then I can put an A3 here, the A2 goes here, and the A1 goes here, and we are done. We've got our multiplication table. And this is, I believe, the field group. This is V. I think it's V or it's K4 are the terms. I think sometimes I always put V4, but it's the Klein group, the Klein 4 group, not to be confused with the musical group, the Klein 4 group, who do math-based songs. They're very nice to listen to. All right, so we've already got the multiplication table out of the way. That's good. I assume that would be worth a mark or 2, just having that worked out. I don't think you really need to explain it. If you do, just put my reasoning into words. You can't have A2 times A1 couldn't be A2, because that's already spoken for. It couldn't be A1 or A0, so it's got to be A3, and basically everything else follows from there. Okay, because in the Latin square or Cayley table for a group, you only have one element in each, or one copy of each element per row and column. Okay, that's a nice little rule. It only works if you're dealing with quasi-groups. And a group is a quasi-group. Okay. But what did they want me to do? They want me to prove the whole thing's commutative. Okay. How are we going to do that? How indeed can we do that? So I need to talk about AI, AJ. Now groups are closed. So this is equal to sum AK for. So, well, let's be a little nice. So let's say fix an A, fix an I and a J. Then, since groups are closed under multiplication, What that means, if you multiply two elements in the group, you get another element in the group. So we can find k. So AI times AJ is equal to AK. I want to show this is the same k you would get if you did AJ times AI. And it's true up here. We actually didn't need to use the property that it's commutative to fill this in, because the same reasoning tells me A3's got to be there because the A1, A0, and A2 here. So it sort of happens to be true here. I didn't need to use commutativity, but I want to show that it's got to be that way. The thing is, I don't know what I and J are. I don't know what K is. I don't have a whole lot of information. In fact, the only thing we really know is, regardless of what K is, the square of this element is a naught. So I guess AI, AJ, and then you multiply by AI, AJ again. That's AK times AK. That's a naught. So AI, AJ is its own inverse. Okay. Multiply it by itself and you get the identity. That's what it means to be an inverse. It's self-inverse. But using sort of the inverse formula, AB inverse is always B inverse A inverse. I can see another expression for this inverse is this, but AJ is its own inverse and AI is its own inverse. Every element is its own inverse. That's the property I exploited up here, and I'm using that down here as well. And so the conclusion here is AI, AJ, you just follow sort of this sequence of equalities, must be the same as AJ, AI, and that's exactly what we were asked to prove. Okay. Not a bad group theory question. I sort of went through that quickly, but I do like group theory, and I don't get to do enough of it. So there we go. You would probably actually want to do that proof that it's commutative first, and then say, by the way, here's the multiplication table. But I think that's it. I just want to double check there wasn't anything else I have to prove. Prove it's commutative. That's it. All right, so this has been a sort of fun little trip back in time, I guess. 1968 paper, very interesting to look at. Different questions, certainly. I mean, we don't do group theory in high school anymore, at least not most places, I would say. And there was a lot more, you know, calculus-y stuff, and certainly conics, the parabola question, the ellipse question. The conic sections are not focused as much. So it's very interesting to see how things have shifted over time. Kind of nifty. So hopefully you guys enjoyed this little exploration. I certainly did it. I like these 13 questions. Of course, remember, we only needed to answer 10 of them, but I think we all did well there. Okay, so thank you guys so much for watching. If you like weird sort of things like this, I can try and find some other interesting, obscure contests. Feel free to leave a comment down below. And as always, feel free to subscribe or like, or if you got a different way to do a question, I'm more than eager to see or read your way of doing things. But I think that's it for me for now. Thank you so much for watching again, and have yourself a wonderful day.